In this video, we're going to talk about reactions of alkenes. Let's start with this example. Let's say we have one pentene, and let's react it with hydrobromic acid, HBr. What's going to happen in this reaction? This reaction is an electrophilic addition reaction. HBr will be added to the carbon atoms across the double bond. The hydrogen atom is going to go on the primary carbon. This carbon is primary because it's attached to only one other carbon. The bromine atom is going to go on a carbon that is secondary. The secondary carbon is more substituted. It's attached to two carbons. This reaction is regioselective. The bromine will selectively be added to the carbon that is more substituted, the carbon that is attached to more carbon atoms. And we're going to talk about why. So this reaction proceeds with Markovnikov addition. There's another reaction that's similar to this one that proceeds with anti-Markovnikov addition. It's when you mix HBr with peroxides and you react it with an alkene. In this case, the bromine atom is going to go on the primary carbon as opposed to the secondary carbon. So the second reaction proceeds with anti-Markovnikov regiochemistry. The idea of regioselectivity has to do with where the bromine atom goes, which region of the molecule is going to react with. So this will be considered a regioselective reaction. Now let's go over the mechanism for the first reaction. The alkene in this reaction is the nucleophile. A nucleophile is a molecule that is electron rich. It can donate a pair of electrons. HBr is going to be the electrophile in this reaction. It's going to accept a pair of electrons. The nucleophile is like the Lewis base. The electrophile is basically the Lewis acid. Now to show the mechanism, the arrow is always going to start from the nucleophile and it's going to go to the electrophile. Now the reason why the nucleophile, in this case the alkene, is going to react with the hydrogen in HBr is because hydrogen is partially positive, bromine is partially negative. Bromine is more electronegative than hydrogen. As a result, you have unequal sharing of electrons in this bond. Because bromine is more electronegative, it's going to pull those electrons in that covalent bond closer to itself. And so bromine is going to acquire a partial negative charge. Hydrogen is going to be partially positive. So it's going to be deficient in electrons. The nucleophile, being electron rich, is attracted to this partially positive hydrogen atom. And so it's going to react with the hydrogen part in HBr. Now the arrow represents the flow of two electrons. What's going to happen here is the pi bond is going to break. And those electrons will be used to form a new bond between the primary carbon and the hydrogen. Now here's a question for you. Why does the hydrogen go on the primary carbon and not the secondary carbon? Why should we put the hydrogen on the primary carbon? If we put the hydrogen on a primary carbon, we're going to get a secondary carbocation. If we were to place the hydrogen on a secondary carbon, we're going to get a primary carbocation. Now the reason why this doesn't happen is because primary carbocations are less stable than secondary carbocations. So you need to know that tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations. So the reason why the hydrogen goes on the less substituted carbon is because it forms a more stable carbocation intermediate. Now let's go back to the reaction. So after this pi bond breaks, those electrons are used to form the bond between carbon and hydrogen. And in order to form a bond between carbon and hydrogen, this bond must break as well. Now because bromine is more electronegative than hydrogen, when this bond breaks, the electrons are going to go towards the bromine atom. Initially, before that happens, bromine has 3 lone pairs. Now it's going to have 4. So here we have our secondary carbocation intermediate with our newly formed CH bond. And now we have the bromide ion in a solution next to the carbocation. Now the bromide ion has a negative charge, and we know opposites attract, so it's going to be attracted to that positively charged carbocation. So to show the mechanism, we're going to draw the arrow from the nucleophile to the electrophile, from negative to positive. So bromine is going to use a lone pair, or 2 electrons, to form a sigma bond between the secondary carbon and itself. And so this is how we're going to get the final product. By the way, every single bond contains a sigma bond. A double bond has 1 sigma bond and 1 pi bond. A triple bond has 1 sigma bond, 2 pi bonds. Sigma bonds are stronger than pi bonds. It's easier to break a pi bond, but it's harder to break a sigma bond. So alkenes are therefore quite reactive because they carry a pi bond, which is relatively easy to break. Now let's go back to this part. The bromide ion can attack the carbocation in 2 different ways, from the front, or it can attack from the back. Because it can approach the carbocation in both ways, we can get a mixture of products. So we can get both the R and the S isomers in this reaction. So this reaction is regioselective because the bromine atom will selectively be added to the secondary carbon and not the primary carbon. So we have a regioselective reaction. Now, this reaction is not stereoselective. There's no specificity in this reaction because we get a mixture of stereoisomers. We don't get one stereoisomer over the other. We get both. So it's not stereoselective, but it is regioselective. Now let's work on some practice problems. Go ahead and predict the major product for each of the following reactions in this example. Feel free to pause the video and work on these examples. So what will be the major product for the first example? Where will the bromine atom, where is it going to go? Whenever you mix HBr with an alkene, the bromine atom is going to go on the more substituted carbon atom. So this carbon is secondary because it's attached to 2 other carbon atoms, and this one is tertiary because it's attached to 3 other carbon atoms. The double bond is going to turn into a single bond because this is an electrophilic addition reaction. The hydrogen is going to go on a secondary carbon. The bromine is going to go on a tertiary carbon. This reaction is regioselective. It proceeds with more carbon-to-carbon addition. For the next one, the same is true with HCl. The chlorine is going to go on the more substituted carbon atom. This carbon is primary. It's attached to one carbon. And this carbon on the other part of the double bond is tertiary. It's attached to 3 other carbon atoms. So we're going to break the double bond and put the chlorine atom on the tertiary carbon. There's no need to show the hydrogen in this example. You can just leave your answer like this. Now, this carbon atom here is not chiral because this side is equivalent to that side. For this carbon atom, it's not chiral either because we have 3 identical methyl groups. So we don't need to show stereochemistry for the products of the first 2 examples. For the next example, where will the iodine go? Will it go on this carbon or on this one? So this carbon here is secondary. It's connected to 2 other carbons. This one here is tertiary because it's attached to 3 different carbon atoms. So this reaction is regioselective. It's going to proceed with more carbon-to-carbon addition. So the iodine atom is going to be added to the tertiary carbon. Now, once we add it to this carbon, will it be chiral? Is this carbon atom here chiral? This carbon atom, would you say it has 4 different groups? That's the question. I would say yeah. Once we place, let me put the iodine atom here. Once we put it here, we're going to have a chiral center. This carbon is secondary. It's different from this carbon, which is tertiary, and this one is secondary. These 2 secondary carbons are not identical. The one on the left is on a 6 carbon ring, the other one on the right is in a 5 carbon ring, and so they're different. So we have a carbon with 4 different groups, so we have a chiral center, which means we need to show stereochemistry. The iodine atom could be on the wedge, or it can be on the dash. So we need to show both because we get 2 different products. With stereochemistry involved. Now, what about reacting this particular alkene with HBr in the presence of an organic peroxide? A peroxide is basically 2 oxygen atoms connected by means of a single bond attached to 2 other R groups. So this is an organic peroxide. It reacts in a similar way as hydrogen peroxide. So if you were to see ROOR or H2O2, they will have the same effect when used in connection with HBr. So first we need to determine which carbon atom the bromine atom is going to go on. This carbon is primary, this one is tertiary. When you have HBr in the presence of a peroxide, we know the reaction is going to proceed with anti-more carbon-to-carbon addition. So the bromine atom is going to go on the least substituted carbon atom of the double bond. So that is, it's going to go on the primary carbon. So this is going to be the major product of the reaction. And this carbon is not chiral, so we don't need to indicate stereochemistry for this example. Let's work on this example problem. How many different products are formed when 2-pentene reacts with hydroboric acid? Well, let's find out. So first, let's draw 2-pentene. So we're going to draw a pentane, which is a 5 carbon chain, and then we're going to put the double bond between carbons 2 and 3. So this would be 2-pentene if we count it this way. So now let's react it with HBr. This reaction is not regioselective because both carbon atoms across the double bond have the same substitution. They're both secondary. So the bromine atom can go on either one. Thus, we're going to get an equal mixture of 3-bromopentane and 2-bromopentane. So we're going to get these two different products. Now, the goal of this problem is to determine the number of different products. So we need to take into account stereochemistry. This carbon atom is not chiral because we have two identical ethyl groups. So therefore, we only get one product of this type. Now, 2-bromopentane does contain a chiral center. This carbon has 4 different groups. It has a bromine atom, it has a hydrogen, it has a methyl, and it has a propyl group. So this is a chiral center, which means we can get 2 different stereoisomers of 2-bromopropane. So taking stereoisomers into account, we get a total of 3 different products. So that's it for this problem. Number 2, draw the major product formed from the reaction between 3-methyl-1-pentene and hydrobromic acid. So let's begin by drawing 3-methyl-1-pentene. So this is pentane, and we're going to put a double bond between carbons 1 and 2. And then we have a methyl on carbon 3. Now let's react this with hydrobromic acid, HBr. Now you might be thinking, okay, we need to break the double bond, and we need to put the bromine atom on the more substituted secondary carbon. And if you're thinking that way, that's a good start, but it turns out that this is not going to be the answer. Even though we know this reaction will proceed with Markovnikov regiochemistry, and it's preferable to put the bromine on the secondary carbon as opposed to the primary carbon, we do have a tertiary carbon adjacent to the alkene, or to the double bond rather. And so what we're going to get is a carbocation rearrangement. Thus, in order to get the right answer, we need to show the mechanism for this problem. The nucleophilic double bond is going to react with HBr. The pi bond is going to break, and we're going to form a new sigma bond between the primary carbon and the hydrogen. So this is going to create initially a secondary carbocation intermediate. Now whenever you have a secondary carbocation adjacent to a tertiary carbon, what you're going to get is a hydride shift. The hydrogen on the tertiary carbon is going to shift towards the secondary carbon. As it leaves the tertiary carbon, it's going to leave behind a positive charge. And so now we have a more stable tertiary carbocation intermediate. Now once this intermediate forms, the bromide ion is going to react with it. And so this is going to be our major product. 3-bromo-3-methyl-pentane. Now these two ethyl groups are identical, so stereochemistry is not relevant in the product of this reaction. So this is going to be the answer. Now I want to take a minute to talk about the textbook definition of Markovnikov's rule, because we described it in terms of carbon atoms as opposed to in terms of hydrogen atoms. In fact, the textbook definition of Markovnikov's rule is that the H plus in HCl or HBr, that's going to go on the carbon with more hydrogen atoms. So in this case, that's going to be the primary carbon. The primary carbon has 2 hydrogen atoms. The secondary carbon has 1. So according to Markovnikov's rule, this hydrogen is going to go on the carbon with more hydrogens. So once this double bond reacts with HCl, we're going to put the hydrogen on the primary carbon. And we'll get the plus charge on the secondary carbon. So that's the textbook definition of Markovnikov's rule. But the end result is that the chlorine is going to go on the more substituted carbon atom of the double bond. When taking a test, it's easier to view it in terms of carbon rather than hydrogen. It's easier to identify which carbon is more substituted across that double bond than counting the number of hydrogens. So I just want to make sure you're aware of that's how Markovnikov's rule is described. It's basically the addition of the H plus to the carbon atom that's part of the double bond that has more hydrogen atoms. So now let's work on another example. Let's react this alkene with 1 mole of hydrobromic acid, or we could say 1 equivalent of HBr, and 2 equivalents, or 2 moles, of sodium iodide. What's going to be the product of this reaction? Feel free to work on this example. So the first thing that's going to happen is the alkene is going to react with hydrobromic acid. According to Markovnikov's rule, the hydrogen is going to go on a primary carbon because that carbon has the most number of hydrogen atoms across the double bond. And initially, we're going to get a secondary carbocation. Now, that secondary carbocation is adjacent to a tertiary carbon. So what's going to happen next is a hydride shift. So now we're going to get a more stable tertiary carbocation intermediate. Now what's going to happen here? We're going to get 2 different products. One possible product that we can get is that the bromide ion could react with the carbocation. If that happens, we're going to get this product. Now we also have iodide in a solution. So iodide could also react with the carbocation. So in this example problem, we're going to get a mixture of products. The question is, which one is going to be the major product? The only way to answer that is to look at the concentration. The concentration of iodide is greater than the concentration of bromide, because in the beginning we were told that we have 2 equivalents of sodium iodide and only 1 equivalent of HBr. Therefore, based on concentration, this is going to be the major product, and this will be the minor product. Now let's consider some other reactions. So starting with 3-methyl 1-pentene, let's react that particular alkene with H3O+, the hydronium ion. We're also going to react it with, this is a separate reaction by the way, BH3 boron, not boron, but borane, with THF, tetrahydrofuran. And in the second step, we're going to have hydroxide, hydrogen peroxide, and water. And then for a third reaction, in the first step, we're going to have mercury acetate with water, followed by sodium borohydride, NaBH4. So what's going to happen if we mix this particular alkene with H3O+? When H3O plus reacts with an alkene, it's going to form a carbocation intermediate. As a result, it's subject to rearrangements. Now, this particular alkene has the ability to rearrange because we have a tertiary carbon adjacent to a secondary carbon that's part of the alkene. So we're going to get a hydride shift, and the end result of this reaction is going to be a tertiary alcohol. So this reaction proceeds with Markovnikov addition, but it's subject to rearrangements. The OH is going to go on typically the most substituted carbon atom that's adjacent to a double bond. Now for this reaction, hydroboration oxidation, this reaction proceeds with anti-Markovnikov regiochemistry. The OH is going to go on the least substituted carbon atom. In this case, the primary carbon. For the next reaction, we have oxymercuration, demercuration. The hydroxyl group is going to go on the secondary carbon. It's going to go on the most substituted carbon of the double bond. So this reaction proceeds with Markovnikov regiochemistry. However, it does not rearrange. So here we're going to get a secondary alcohol instead of a tertiary alcohol. So make sure you know the differences between these three reactions. So this one proceeds with anti-Markovnikov regiochemistry. The OH is going to go on the least substituted carbon of the double bond. This one proceeds with Markovnikov regiochemistry. The OH is going to go on the most substituted carbon atom of the double bond. And for this one, it's susceptible to rearrangements. So it really depends on the structure of the alkene. So let's say we have this particular alkene. And we're going to react it with water and sulfuric acid. What's going to be the major product of this reaction? The first thing you need to realize is that sulfuric acid is a strong acid. When it reacts with water, water is going to act as a weak base. So sulfuric acid is going to donate a proton to water, creating H3O plus and the bisulfate ion. So this reaction produces H3O plus. So mixing an alkene with water and sulfuric acid is equivalent to reacting it with H3O plus. Now the first thing that's going to happen is the alkene is going to react with a hydrogen in H3O plus. Now here's a question for you. On which carbon atom will the hydrogen go? Will it go on carbon A or carbon B? Both carbon A and carbon B, they're equally substituted. They're both secondary carbons. So which one will it go on? In this case, Markovnikov's rule won't help us. Because they're both secondary, they both have the same number of hydrogen atoms. But the hydrogen is going to go on carbon A. The reason for that is the plus charge wants to be next to the quaternary carbon, because a methyl shift can occur, giving us a more stable carbocation intermediate. Right now we have a secondary carbocation intermediate. But once we move the methyl, we can get a tertiary carbocation intermediate. The driving force for these carbocation rearrangements is stability. The carbocation will rearrange in such a way until it finds the most stable form that it can acquire. And so we're going to get this methyl shift. So this arrow is going to start from this bond, the 2 electrons in this bond, and it's going to point towards the carbocation. And so the entire carbon-carbon structure is going to change. My drawings are terrible. I need to do this better. So now this carbon atom, it lost a bond. That's where the plus charge is going to be. So right now what we have is a tertiary carbocation intermediate. We went from a secondary carbocation to a tertiary carbocation. And now at this point, water can react with the tertiary carbocation. And what we're going to get at this point is something known as an oxonium ion. And then we're going to use another water molecule to remove one of the hydrogens, and this will give us an alcohol. Now, this carbon here, it's a chiral carbon, and water could attack from either side. So we can get a mixture of isomers here. But we're not going to worry about it too much, so I'm just going to put OH. Just know that we can get a mixture of stereoisomers. So that's going to be the major product for this particular reaction. Go ahead and try this one. What's going to be the major product if we react this alkene with dilute sulfuric acid in methanol? So methanol is a solvent in this reaction. What's going to happen here? Sulfuric acid can give away a proton. And that's what's going to happen. The alkene is going to acquire a proton. Now this proton can come directly from sulfuric acid, or it can come from a protonated solvent molecule. So just as water can react with sulfuric acid, methanol can also react with sulfuric acid. And we can get the conjugate acid of methanol and HSO4. So this alkene can acquire a proton from that species as well. So there's more than one way to show the mechanism. Just keep that in mind. So regardless of where the alkene gets the proton, we're going to end up initially with this secondary carbocation. Now what do you think is going to happen next? Well, we do have a tertiary carbon here, so we could get a hydride shift. But notice that we have a 5-carbon ring. Whenever there's a potential for a rearrangement, and if you have a 5-carbon ring, there's a possibility that you can get a ring expansion. A 6-carbon ring is more stable than a 5-carbon ring. A 6-carbon ring has less angle or ring strain. So that's what's going to happen here. We're going to get a ring expansion. Let's call this carbon 1, 2, 3, 4, and 5. So the sigma bond between carbons 1 and 5, that's going to break. Those electrons will be used to connect the secondary carbocation, which let's call it carbon 0. So the electrons between carbons 1 and 5 is going to connect carbon 0 and carbon 5. And so we're going to get a 6-carbon ring, which is going to look like this. Now let's call this carbon 5, carbon 0, 1, 2, 3, 4. Carbon 0 has a methyl group attached to it. Now, which carbon atom has the plus charge? Is it carbon 0, 1, or 5? So we lost the bond between 1 and 5, but we formed a new one between 0 and 5. So carbon 1 lost the bond, and it didn't get anything back. Thus carbon 1 has the plus charge. So right now what we have is a secondary carbocation. So far, the stability has been improved. Here we had a secondary carbocation with a 5-carbon ring. Now we have a secondary carbocation with a 6-carbon ring. So we have a structure that's more stable than the previous one. But we're not done. Another rearrangement can occur because we have a tertiary carbon adjacent to a secondary carbocation intermediate. So a hydride shift is going to be the next thing that's about to happen. So after this hydride shift, we're going to have a 6-carbon ring with a tertiary carbocation intermediate. And we really don't need to show the hydrogen here. So now the next thing that's going to happen is methanol is going to react with the carbocation intermediate. And so we're going to get an oxygen with a plus charge and 3 bonds. Now another methanol molecule is going to remove this hydrogen, and the end result of this reaction is an ether. So that's what happens when you react an alcohol with an alkene. You're going to get an ether. So now let's work on this synthesis problem. Consider the following ether. Actually, let's make this a C. What alkene and what alcohol can you use to make this particular ether? Feel free to pause the video if you want to. So in order to determine the type of alcohol and alkene that you need to know where to split the molecule. And you want to split it basically at the carbon-oxygen bond. So we could split it here or here. But let's focus on splitting it here. So this part has the oxygen. That's where the alcohol is going to be. So I'm going to redraw the right side first. That is this part. I'm going to draw everything that I see here. I'm just going to add a hydrogen to the oxygen. So let me put that in a different color. So here's the hydrogen, and then the oxygen, and I'm going to draw exactly what I have here. Now the other part is going to be the alkene. And I could put the double bond either here, here, or here. So let's put it here. In order to put it here, I need to take off a hydrogen. So it's going to be CH2 instead of CH3. So this is one possible combination. If we react this alkene with this alcohol, we can make this particular ether. Now, if I were to put the double bond here, it would look like this. So I'm going to take a hydrogen from CH2, so we're now going to have CH, double bond C, and then that carbon has 2 methyl groups, which I can just put here. So if I were to react this alkene with this alcohol, it would give me the same product. Now keep in mind, we still need an acid catalyst to accelerate the reaction. So we would need H2SO4, dilute H2SO4, to get this reaction going. Now let's see what's going to happen, or what type of alkene and alcohol that we could use if we were to break the bond here. So if we were to break it there, this would be the alcohol that we're going to start with. So we're going to have CH3, CH2, C, and then OH. And here we have two methyl groups. Now we can react this alcohol with two different alkenes. We could put the double bond between those two carbons or between those two carbons. So this is basically a 4-carbon chain that has no branches. If we put the double bond here, this is 1-butene. Or we could react the alcohol with, if we put the double bond here, that will be 2-butene. So this alcohol with 1-butene will give us the same product, or with 2-butene, that will give us the same product as well. So far, we've considered 4 different combinations that could lead to this particular ether. And so that's how you could determine the initial parts that is needed to produce this particular product. Now let's move on to our next problem. So let's say we have 1-methyl cyclohexane, and we're going to react it with mercury acetate with water, followed by sodium borohydride. And let's compare that to another reaction. It's going to be a similar reaction. We're going to use mercury acetate again, but instead of using water, we're going to use ethanol, CH3CH2OH, followed by sodium borohydride. So the first reaction is called oxymercuration, demercuration. The second reaction is alkoxymercuration, demercuration, because we're using an alcohol. Now we know this reaction proceeds with Markovnikov addition. So the OH group is going to go on the more substituted carbon atom of the double bond. In this case, it's going to be the tertiary carbon as opposed to the secondary carbon. So the end result for the oxymercuration demercuration reaction is that we're going to get an alcohol. The nucleophile is water. For the alkoxymercuration demercuration reaction, the nucleophile is not water, it's an alcohol. And whenever you react an alcohol with an alkene, you're going to get an ether. So instead of an OH group, we're going to get this product. It's basically what you see here without this hydrogen. So we're just going to draw OCH2, CH3. So that's going to be the end result of this reaction. Now let's talk about the mechanism of the oxymercuration demercuration reaction. So we're going to start with mercury acetate, which looks like this. Mercury acetate has 2 acetate groups and a lone pair. One of the acetate ions, or one of the acetate groups, can easily dissociate from mercury. And so we're going to get a mercuric cation, which looks like this, and a free acetate ion. Now whenever you see OAC, basically this is acetate, which looks like that. So this is reversible. The acetate can always rejoin with the mercuric ion to produce mercury acetate. So this process goes backwards and forwards. Now once we form this mercuric cation, we can react it with an alkene. So mercury has a positive charge. Therefore, it's an electrophile. the alkene is going to be the nucleophile. And so we're going to draw the arrow from the nucleophile to the electrophile. Now the mercury atom is going to go on the less substituted carbon of the double bond. That is, it's going to go on the secondary carbon. And initially, we're going to have a plus charge here. Now you might be thinking this is a carbocation, but it's not, because we do have a resonance form for this structure. This mercury atom can donate a pair of electrons to the carbon with the plus charge. And so we can get a resonance structure that looks like this. So now mercury bears the positive charge. Now the true intermediate is somewhere between these two structures. It's not a pure carbocation because this intermediate doesn't rearrange like a typical carbocation does. And it's not exactly this structure either, because it does have some characteristics of a carbocation and some characteristics of a three-membered ring. So it's somewhere between the two. So what we're going to do is we're going to draw a resonance hybrid to reflect, or to get a better accurate description of the intermediate of this step. So the resonance hybrid is going to look like this. So since this is the new bond that was formed, we're going to draw a dash for that bond. So the plus charge is not completely on this carbon, nor is it completely on the mercury atom, but it's shared between the carbon and the mercury atom. So what we have here is a partial positive charge on both the carbon and the mercury atom. So this is known as the mercurinium ion. It's the resonance hybrid of these two. So this particular hybrid explains why we don't get a typical carbocation intermediate for this particular reaction. And it also explains why the nucleophile, in this case water, reacts with the tertiary carbon as opposed to the secondary carbon. It's because the tertiary carbon has more partial positive charge than the secondary carbon. And so water is going to attack this carbon. And so this reaction proceeds with Markovnikov regiochemistry. So we'll have our mercury acetate group on one side, and on the other carbon, we're going to get an oxonium species. Now we're going to use another water molecule to take off one of the hydrogen atoms. So going from the beginning to this result, that's the first step. This is known as oxymercuration. The second step is known as demercuration. That's when we use sodium borohydride. So the hydride ion will be used to get rid of the mercury acetate group. It's not going to affect the hydroxyl group. So the end result is that we're going to replace this with a hydrogen. So that last step is known as demercuration. That's where we remove mercury and replace it with a hydrogen atom. But the end result is that we get an alcohol in this molecule. Now let's work on an example problem. Let's say we have two functional groups in one molecule. We have both an alcohol and an alkene all wrapped in the same molecule. And we're going to activate this reaction with a dilute amount of sulfuric acid. What do you think the product of this reaction will be? Well, the first thing that's going to happen is that the alkene is going to receive a proton from either H2SO4 or from a protonated solvent molecule. And so we're going to get a tertiary carbocation intermediate. Now the hydroxyl group, the OH group, is going to act as a nucleophile. It's going to be attracted to the carbocation since it bears a partial negative charge. And whenever you have this intramolecular reaction, you're going to get a ring. Let's call this number 1, 2, 3, 4, 5, 6. So we're going to get a 6-membered ring. So this is 1, 2, 3, 4, 5, 6. On carbon 6, we have a methyl group, and we also have an ethyl group. The oxygen still has a hydrogen attached to it. It lost a lone pair, so it has a 1 left over, and it has a plus charge. So that's what we have at this point. Now a base, this base could be the OH of another molecule. It could be HSO4 minus or something else in the solution. But some molecule is going to act as a base to remove this hydrogen. So the end result of this reaction is a cyclic ether. So whenever you have a molecule with two different functional groups that can react with each other, typically you're going to get an intramolecular reaction, and it usually closes into a ring. So this is the answer for this problem. Now let's work on a few example problems dealing with hydroboration oxidation. So go ahead and predict the products for these reactions. So here we have borane and tetrahydrofuran, and in the second step followed by hydrogen peroxide and hydroxide. Sometimes you'll see it like that, other times you'll see water included, but the end result is still the same. And then we're going to compare the product of that reaction to the product of this reaction. So instead of BH3, we're going to use BD3. Everything else will be the same. So if we don't see water in the second step, the result will still be the same. Go ahead and try these two example problems. So hydroboration oxidation proceeds with anti-Markovnikov regiochemistry. The OH group is going to go on the least substituted carbon atom across the double bond. So in this case, that's going to be the primary carbon. So this is going to be the product of the first example. We don't have to worry about stereochemistry because, as we can see, this carbon atom is not chiral. Now what about the second example? For the second example, we need to talk about that. If you see D is deuterium. It's the isotope of hydrogen. Chemically speaking, they react in a similar way, but they have different nuclear properties. But treat deuterium as if it was hydrogen. The only difference, though, when dealing with deuterium versus hydrogen in organic chemistry is that in line structures, you need to show deuterium. For hydrogen, you don't have to show it. And so that's going to be the key difference there. So let's work on this one step at a time. The first step is hydroboration. That would be BH3 and THF, but using BD3, I'm sure it's going to be called something slightly different. Now, during this step, what's going to happen is we're going to add deuterium on the tertiary carbon, and BD2 is going to go on the secondary carbon. But now we need to highlight the stereochemistry here. So let's say the methyl group is in the front. Deuterium will then be in the back. And BD2 will also be in the back. These two groups are added on the same side. This is called syn addition, when they're added on the same side. To show the mechanism for that, here's what you can do. So we have deuterium, boron, and two other deuterium atoms. Now, hydrogen has an electronegativity of 2.1. Boron is 2.0. So hydrogen is slightly more electronegative than boron. So boron is going to be like the electrophile. It has a slight partial positive charge relative to hydrogen. Hydrogen is the nucleophile. So because boron is relatively electrophilic, the double bond is going to attack boron. Deuterium is going to be relatively nucleophilic with respect to boron. So the bond between boron and deuterium, that's going to be used to connect deuterium with the tertiary carbon. So that's how you can show the mechanism for this first step. Now, in the next step, by the way, during the first step, we get this plus the enantiomer. So I'm going to put plus En for the enantiomer. In the next step, which is oxidation, we're going to oxidize it using hydrogen peroxide, and this is going to occur under basic conditions. So we're going to replace this group with an OH group, and it's going to happen on the same side. So if BD2 is in the back, the OH group will be in the back. So once we replace it, the end result will be this product. Now we can also get the enantiomer, which is going to look like this. So the end result of the hydroboration oxidation reaction is that the two groups that were added, they're added on the same side. So this is a syn addition reaction. And we do get a pair of enantiomers for this particular example. Now let's move on to our next example. So instead of using deuterium, we're going to go back to hydrogen. So in the first step, this is going to be B2H6 in THF. By the way, THF, tetrahydrofuran, is basically a cyclic ether. It's a 5-membered ring with 4 carbons and 1 oxygen. In the second step, we're going to use hydrogen peroxide and hydroxide. So what's going to be the end result of this reaction? Now, if you see B2H6, it's going to have the same effect as BH3. B2H6, this is diborane. It's basically a dimer of 2 borane molecules. So this is how it looks like. So here are the two boron molecules, and two of the hydrogens will be shared by the two boron molecules. And so that's diborane. It's basically BH3 times 2. So it's B2H6. So what do you think the end product for this reaction will be? We know the hydroxyl group is going to go on the secondary carbon. The hydrogen is going to go on the tertiary carbon. So we're going to add hydrogen instead of deuterium this time. The end result for this reaction, with stereochemistry included, is this. So let's say the methyl group. If the methyl group is in the front, the OH will be on the secondary carbon, but it's going to be in the back. And we're going to get the enantiomer as well. So if the methyl group is in the back, and I'm running out of space, so let's put this somewhere else. If the methyl group is in the back, the hydroxyl group will be in the front. Now, if you just look at this the way it is, you may think, well, this appears to be anti-addition because the methyl and the OH group, they seem to be on opposite sides rather than on the same side. But remember, we didn't add the methyl group. What we're adding is the hydrogen and the OH. So right now, there's no hydrogen here, but the product does have a hydrogen. If you show the hydrogen, then you could see that this reaction is syn addition. So these are the groups that we're adding, and those two groups are on the same side. But for multiple choice tests, you won't see the hydrogen. Your answer will look like one of these two. So you need to be aware of that when taking a test on this particular reaction. Now let's go over the mechanism of the hydroboration oxidation reaction. So if we were to react propene with borane and THF, followed by hydroxide, hydrogen peroxide, and water, the end result is that we're going to get an alcohol on a primary carbon. So we're going to get one propanol. But let's show a mechanism starting from this alkene to this product. Feel free to try it if you want to. So in the first step, we're going to react this with BH3, and we can draw it this way. The double bond is going to act as a nucleophile, and it's going to attack boron, which is the electrophile, and hydrogen is going to behave as a nucleophile in this case. So we're going to get this product at the first step. We really don't need to show this hydrogen. Now, this molecule is going to react with another alkene. So I'm going to redraw that molecule here. So we have hydrogen, boron, hydrogen, and then here's the 3 carbons that we added to the first boron group. So this process is going to repeat itself 3 times. And so now we're going to get another alkene, and we're going to react it with the product of this reaction. So the product of that reaction looks like this now. We have 2 R groups on the boron, and it has only 1 hydrogen left over. Maybe it's better if you see it this way. This hydrogen is now here, for those of you who might be curious about it. So now let's react to this alkene with this molecule. So this hydrogen, I'm going to show it right here, is attached to boron, and boron now has 2 R groups. So just like before, the alkene is going to attack the boron atom, and the hydrogen is going to connect with the other carbon. And so now at this point, we have a boron with 3 different R groups. So we have a trialkyl borane molecule. It's trialkyl because there's 3 R groups. So what we're going to do at this point is we're going to take our trialkyl group, I put too many carbons on that part. So we're going to react this with hydrogen peroxide. Now mind you, in the second step, let me just show it here. We have H2O2, hydroxide, and water. So these 2 will initially react. So this is hydrogen peroxide, and we're going to react it with hydroxide. Hydroxide is going to remove a hydrogen from hydrogen peroxide. This is going to produce water and this deprotonated peroxide ion. So this part is going to react with the trialkyl borane molecule. So this is what we now have. There's a lot of drawing for this particular mechanism, so hopefully you'll be patient with me as I draw each step. Now in the next step, one of the alkyl groups, let me actually draw out one of the alkyl groups. So the one that's going to react, I'm going to write it as CH2, CH2, CH3. So this is going to attack this oxygen, expelling hydroxide. By the way, this step is reversible. The previous steps were not reversible. So we're now going to have an oxygen with CH2, CH2, CH3. Now this is going to react with hydroxide. The hydroxide and the ethoxide ions, they're in equilibrium with each other because the ethoxide could leave or the hydroxide could leave. It can go back and forth. But we want to go in the direction that's going to lead us to our product. So we need ethoxide to leave. So ethoxide could spontaneously dissociate from this trialkyl borane group with this OH group attached to it. Well, technically it's no longer a trialkyl borane group since it has 2 R groups instead of 3. So we're going to eliminate this alkoxide ion. So what we now have is a boron atom with 2 alkyl groups and an OH group. And we have a free ethoxide ion group. This ethoxide ion group is going to become our desired product because our goal is to get 1 propanol. So all we need to do at this point is react it with water. So once it's protonated by water under basic conditions, then we're going to get our desired alcohol. And as we can see, the OH group is on the less substituted primary carbon. So that's how we could show the mechanism for the formation of 1-propanol from propene using the hydroboration oxidation reaction.